we had some very sort of basic introduction to the speech production, and now we are going to have the similarly basic, relatively easy introduction, hopefully, to the speech signal analysis. We are not going to be talking about nitty-gritties. I have essentially only two important messages to impart. So again, I apologize to the people who studied speech analysis, who are fluent users of Praat and have done all sort of phonetic extractions of all sort of features that you might find it sort of a little bit slow going, but you're going to be rewarded hopefully in about an hour when we get a little bit to the deep learning. So maybe then the other people will be bored and the other people will get a little bit more excited. So as we were saying earlier, we have our vocal folds produce this type of voice source, which gets filtered to some particular waveform, which is propagated through the air. And I was saying, it's kind of relatively easy to extract these pitch durations, the pulse durations, extract pitch and intensity from this voice source thing. But unfortunately, what we get is the already filtered waveform, which is much more scrambled and much more difficult to analyze, as it were. So yeah, this is what we get when we record somebody. We get already filtered, i.e. scrambled waveform. So yeah, we're talking about this speech waveform. Mathematically, it's essentially a time series of numbers. Usually it's normalized, the numbers are expressed between -1 and 1. If you get numbers over 1 through some recording apparatus, for some reason the waveform gets clipped. Not good. For us it's audible. There are unexpected changes in energy. We hear it as almost small explosions. So yeah, but those numbers between -1 and 1 somehow correspond to the sound pressure level. The positive numbers to sort of higher sound pressure than the ambient sound pressure of the air, and the negative ones, so the lower sound pressure than the ambient sound pressure of the wave. And propagation of these pressure waves through the air is the sound. That's what we perceive as the sound. By the way, we talk about the wave, but unlike some other type of entities which are propagated in some waveform through the air, for example, light, the sound wave is not a wave like this. It's not the wave like the surface of the some sort of water thing or something like that. It's actually just like the atoms or the molecules don't move anywhere. They are just getting more compressed and less compressed. And they sort of bump into each other and they punch that wave through the air. That's why the sound, of course, also that way goes all directions essentially in the air. And we know that they propagate by sort of 300 meters per second roughly. That's how fast it goes. Now, we, of course, when we record something, we need to record this time series. We actually do not record the sound pressure, of course, at every possible instant, but at some particular intervals. Usually the intervals are, we usually record a lot of values per second. How many values per second we record is called sampling rate, and most of the things, most of the recording apparatus and the lot of the data we actually work it are recorded at rather surprising number of 44,100 hertz per second. Many times I looked up the story why this number. I always forget, but it's something to do with the Sony and some particular thing, because that was a sampling rate for the CDs. And it's some particular, it's rather, I told it to my students a few times, but I always forget. So look it up. It's actually somewhat interesting story how these particular things can happen. So yeah, the wave format, WAV format, that saves every sample with some particular resolution, of course. And we use very often the devices like mobile things use the formats like MP4, which are sort of lossy. They compress the sound. Where they sort of, they encode something different than a sample by sample, which they encode it and then the other side decodes it to some resemblance of the wave. So we would prefer for our analysis to have everything saved in this wave format rather than in some compressed format. But we can always decompress. It's not a problem. Now, how can we? So we get this, waveform. A lot of samples here. Imagine that it looks almost like several waveforms, but it's a one waveform. It's just rendered like that. And we want to find out the intensity first. So intensity corresponds somewhat to the loudness. Intensity is objective signal-based measure, while loudness is the subjective, perceived characteristics of the sound, how loud it is. There is, of course, the relation, something more intensive is more loud, but the relation is somewhat nonlinear. We again, and somewhat depends on the frequency as well. We perceive some frequencies more loud than the others. It's a relatively complex thing. I don't think we have to actually worry about that at this stage. We usually extract this signal-based measure called intensity. And for that we use some resemblance of some sort of formula which looks like this. It's a simple formula, take my word for it. It might look a little bit scary. There are some, it doesn't render very well. So this should be an integral. Here, we were talking with Rianku how this transformation from one system to the other. This should be integral, and this should not be there really. But all the other things are more or less correct. So what matters here is that you have to pick some little window. Again, because we need to kind of capture how much energy there is in a signal, and at any given time moment, it's very difficult to say how much energy there is. You need a little bit of a stretch, because energy is there in the pumping of the sound, not indirectly in some particular level. So you take some stretch and calculate how much energy has been exerted in order to produce that sort of pattern of sound pressure changes. And you use this formula. The formula might look a little bit scary, but it's just a formula. You don't need to know what it says. You just fill the numbers in, press the button, and some system calculates that. So, and then of course, so we take some window, and then we slide. So, this just shows the example of some sort of intensity calculating device if we had one. So we take some window, the formula tells you to square it. You square it. By squaring means that positive and negative numbers all count. Because negative square is positive. So whether you go up or down, it counts. And then you sum it, that's what the formula tells you. And then you divide it by something. And for this entire window, you get this one value. That will be projected here. And then you shift the window a little bit and calculate another value. And you join them all together here, and you get some sort of intensity measure, as it were. This particular SPL stands for sound pressure level. That's given in decibel. It's a logarithmic unit. You've probably all of you heard about that. So 10 decibel increase in sound pressure level means 10 times more energy. Not 10 more energy, but 10 times more energy. So if you have sound pressure level, or let's say 50 decibel, about some threshold, 50 decibel, and you change it to 60 decibel, there's going to be 10 times more energy. So if you shift it then to 70, there's going to be 100 times more energy than it was in a 50, etc., etc. So that's why I would say that all of these hum around us, their conditioning gives us something like 40, maybe, decibel around ambient noise, 30, 40. Me speaking, of course, adds another few. 70, 60, 60 is fine. The normal street, well, maybe street in India is 70. 80 starts getting real loud. 90 starts getting painful. 100, 110 is almost that start hurting. Like that may cause damage. So it goes up pretty fast. 10 decibel also increase corresponds to it's 10 times more energy, but it corresponds to doubling the perceived loudness. That's how the relationship between perceived loudness and intensity is sort of nonlinear. Okay, it's written here. So for a given waveform, now, but it's calculated formula. So for any given waveform, if you have some particular signal processing tool which implements that formula, you just give it there and it calculates you the intensity envelope. There are a few caveats we might want to be aware as phoneticians, in particular if you do the very, very small things, because we calculate the average energy over the window. So, you know, the wider the interval, the more smooth the curve, final curve is. But of course it means there is sort of a smearing. When something like this happens, that I'm quiet and say, ka, no energy, and all of a sudden there was this burst. So, but if I calculate the energy envelope and I use kind of wide window, it would show as if there was already some energy before I actually released the ka. So there is this smearing. Sometimes it doesn't really matter. For some very, you know, precise temporal analysis, this might be very crucial. We want to measure onset of this ka, for example, somewhere, and we want to really measure it to 1 millisecond, then we have to think about this very carefully. Of course, if we have the very narrow window, the changes are going to be very dramatic. You know, every vowel, even during the vowel, if the window, of course, width is shorter than the pulse, then we will get this pulsing curve. So this is a lot of balancing act. But once you decide, you just get a formula, press the button, off you go. Curve you have. And the curve is correct, given that window. No place for error. Easy. That's what I mean. Now, what about fundamental frequency? That's a bit more complicated. So this is a little look at now few pulses which are still discernible in this particular fundamental frequency, this particular waveform. So we can indeed, I think if I press something, yeah, this is, I just actually hand drew this. So this is superimposed, presumed pulses, the voice source pulses behind that. So, you know, if we know, if something looks this pretty, we can probably calculate similarly to those other pulses the duration of the source, or duration of the pulse, as it were. You know, 0.005, so that's 200 hertz. Is there something to press, maybe? At some point there will be 200 hertz. So this is higher pitch voice than the ones we were looking before. Maybe here you can see again I did extracted, I measured diligently, and this is 22.7 actually millisecond, 1 over, so 270 hertz. Let's see what happens if I thought that there was that.
Voila.
That was one of those. Fire.
Voila.
You can see it's a female voice, so it starts about 200 and goes almost doubles its frequency towards the end. This is a pulse length. As long as you can see the pulse length like this, you are fine. You can extract it. But it's not always that simple how to extract the pulse length. So there are all sort of different methods, but the most used method is this called autocorrelation method, which works roughly like this. So you again take some little window take some portion of the waveform, and you make it copy, right? And now you know, it's a copy. Now you sort of match them. You put them on the top of each other, as if, you know, these algorithms. So don't take it too literally. There is a mathematical way of doing that. But in principle, it works like this. You put it on the top of that, and then you shift it a little bit. Now you shifted the waveform, and now you look at it sort of. Like, of course, we now see that it's a shifted because we are clever. But if you ask the machine to compare literally point by point, it will see, you know, here this one is high, this one is low, this particular. If you let it compare point by point, we use a correlation between those things. Yeah, at this point, the non-shifted one is high, the shifted one is low, not very similar. You know, here they might be a little bit similar, but no, overall, not very similar. Now shifted another millisecond. Not really very similar, although there might be some spurious similarity popping up every now and then because there are other frequencies, but maybe not so similar. another millisecond, another again and again, until you shift it by 5 milliseconds, and bingo. All of a sudden, they again merge to a pattern which is much, much more similar. So if we represent this in terms of correlation, so we can quantify the similarity. 1 perfect match, -1 exact opposite, and then 0 no relation, anything in between. So we would get the correlation here perfect, trivially. Then correlation going down, 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 up, 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 until high correlation again. So when we find the amount of the shift by which we get back to the something very close to the original form, we found the pulse. We found the distance of the pulse. So the pulse length, I shifted it 5 times, 5 milliseconds, 5 times by 1 millisecond, 5 milliseconds, 200 hertz, like that. This is all good. We can implement it in terms of some particular algorithm. Again, something similar. Take a waveform, take the interval, put the interval, this is the blue thing, put the blue thing, create this sort of red copy, and shift it back and forth a little bit. Here you calculate sort of, this is the shift, amount of the shift for each time spot, amount of the shift and correlation. So you can see that it, 1 perfect match, when you don't shift it, correlation goes down, goes a little bit up, and then goes to here, then goes down, down, oops, then goes down, 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 and it goes very high again after this little thing. So you say, okay, this is the length of the pulse. The correlation gets really very high. Cool. So again, and then you shift a little bit the window, shift the copy, and find where it correlates the best. Shift the window, shift the copy, da da da, like that. This is not a formula. This is an algorithm. This is tricky. Why is it tricky? This is actually an important picture here. You know, we had a very, very good match. Of course, perfect match at the beginning. Now we go, it went to the sort of negative correlation. If you can see, oops, there are these negative numbers here. This is like kind of upside down. And then it got to this correlation 0.2, the peak. And then it started going bad again. So what, 0.2, is it a good one or a bad one? We don't really know. It goes back to 0.5 almost here. Is it a good one or a bad one? We don't know. We waited until it went up to 0, almost 1, and then we need to put some threshold about which we accept that this is repetition and not some spurious similarity. And if we put the threshold wrongly, you know, the algorithm might detect some other ones. But look, like if I then shifted it by, again, that amount, it got very highly correlated again, of course. Because, of course, twice the pulse you shift, it gets correlated again. So if this one, for some reason, there was some little blob, ended up below the threshold, the algorithm would keep going until it finds this one, until it goes over the threshold. Again, so it would actually think that the pulse is twice as long. So the frequency is actually half to what it really, the fundamental frequency is. So this is prone to all sort of issues, this type of algorithm. So it's a process rather than a formula. Many things can and often do go wrong with this process. And this is very, very important message, that we have to be aware that whatever signal processing tool we use, which we use to extract F0, can potentially be wrong. I've seen, unfortunately, many students, but also eminent phoneticians work, who claim some particular super interesting and excellent result, and when you look more carefully, almost everything was down to these F0 extraction errors. So one has to be always careful. So we can get sort of false, sometimes we can get some particular regularity in the signal, which is not really in the voice, but in something else. For example, as everybody who did some field recordings and many other people know, one of the things sometimes people do, that apparently with some recording apparatus, that they put the whatever recording device or whatever some wire goes over the source, which comes from the mains. And of course, in the mains, in India and all over the world, there is this alternative current. Things are changing with a frequency of 50 hertz. 50 hertz, unfortunately, it sort of keeps changing polarity at 50 hertz. 50 hertz, unfortunately, is the speech-like frequency. It's a very low, but it's still fundamental-like frequency. And this might actually, whatever is an electric wire, might impose some particular 50 hertz frequency sort of band, which then means that whenever, for example, nobody's speaking, your system tells you it's 50 frequency voice. And sometimes it interferes with all the other things. There are many other potential issues, but these things are very, very, very sort of prevalent. Now I completely lost idea about time.
4:23.
4:23, excellent. There are, of course, all the other things, like in many people speak with what I refer to creaky voice, which is like vocal fry. Sometimes people speak like that. It's very common for some particular reason in Finland. It became sort of mannerism of some sort. It's a very prevalent, I think the Finns signal some particular type of attitudes using the creak, and usually towards the end of the sentence, the end of the utterance is produced with a creaky voice. And of course, creaky voice means that the vocal folds vibrate irregularly. That of course means that there is no fundamental frequency. But because the algorithm is forced to find something, it finds some spurious jumps. It finds some particular type of fundamental frequency. So there are all sort of other issues. This is one of the examples. There is, for some particular reason, is a Portuguese statement. So this is the first screen print from Pratt. So how many of you, by the way, have used Pratt before? Has everybody used Pratt before? Excellent. Yes. So you know what you're looking at. This is a standard interface of Pratt. This is the waveform here, and this blue line here is a F0 contour. Important thing what I told you, of course, when we slide this window, which we wiggle, slide, wiggle, slide, wiggle, when we join all of those frequencies which we derive from the pulse length, together we get a contour, F0 contour. It's a bit of an imaginary continuous line, but because the F0 doesn't change, it changes here. The pulse length is the smallest value by which it can change, but anyway, so this is the F0 contour. So this here looks at some unvoiced bits here, it's fine, but it looks like the person sort of really suddenly the fundamental frequency jumped from whatever it was here, 300 hertz to 150. Looks like this. Did she really do that? Let's see.
Apartamento novo do Pedro. Você viu o apartamento novo do Pedro?
There was the Sevilla here.
Você viu o apartamento novo do Pedro?
Perfectly good hike in the thing. So this is just a miscalculation. This is what octave jump. Octave jumps are the biggest nightmare of anybody who works with F0. These, in particular, this type of octave jump, when you have the frequency, happens that, that you simply, like when you shift it by one pulse, the correlation is not good enough for the algorithm, so shifts it again. So we think that the pulse is twice as long as it really was, because there is that frequency twice as long, of course. That's harmonics, but it sort of ignores the fundamental frequency and picks the first. Well, not in this case. It sort of takes the half anyway. So, yes. So these octave jumps, there are ways how to avoid the octave jumps, of course. Some of the important things is that usually for the algorithms, you tell it what are the frequency values sort of realistic for this particular portion of speech or this particular speaker. So it means when you say that this is a male speaker, you think, so the male speaker is not particularly sort of deep voice male speaker, so it's going to be something from, let's say, 75 to, like something like me, something from 75 to we want to be careful, to 250 or something like that, That range then limits by how this autocorrelation is shifted, how much is shifted. It only shifts it to within the range which corresponds to those values. So it will never think that I would, speak with a 400 hertz frequency. That is not a candidate, or doesn't think that I would speak with 40 hertz frequency. But if you sort of then pick somebody else, for example, some female speaker or young female speaker whose real fundamental frequency is about 300 hertz, and you run it through this setting of the algorithm, you will get almost the entire F0 contour wrong, or very jumpy. When she crosses down to that range, which she will, of course, then the value is correct, and then it suddenly jumps to the half or whatever. So one has to be careful. Very often when we process F0 for a big corpora, one of the first things, we will talk about this again tomorrow, is that we, for example, decide on the gender or the biological sex of the speakers. Because we need that information for finding the interval, F0 interval processing, which is appropriate for extraction of the things. Usually things like Pratt has a very wide range set up as a default. I think Pratt default is 50 to 600 or something. And that, of course, makes things very, very volatile, very prone to do the octave jumps. There are, of course, algorithms which try to, there is one built in Pratt which try to sort of minimize the amount of octave jumps, because we can see it, this is silly, this shouldn't happen. So there is a way how to algorithmically build it that, don't allow these sudden jumps. But that, in my experience, actually does more harm than good. It just means that the wrongly analyzed areas get more and longer. So just we have to work with the good signal and with the range, which is allowable. Or then not really. If you have very noisy signal, then unfortunately you might need to give up on F0. That's one of the issues. Now, here I had a plan that we will all a little bit play with Pratt. That you will all install it, and I will sort of take my Pratt, and we will sort of look at things together. But it's somehow technically not that straightforward. So let's a little bit keep looking at the Pratt picture, and then we take a break. And then I will talk about other way of analyzing speech signal, which is kind of not Pratt-like and not sort of standard signal processing-like thing. Of course, as you can see here, most of you know, this is a default picture of Pratt. I don't exactly know what this says. It says in Slovak, so it's me, probably, and this is my F0 contour, probably more or less correct, looks quite nice. This yellow line is the intensity. As you can see, intensity closely corresponds to what we call the speech signal envelope. So there would be something if we draw something around it, but it's not identical. And this is a spectrum analysis, maybe not default setting. I just wanted to show something more. You can see formants forming here. Formants are shown as the sort of darker areas in the spectrum. And spectrum, so this would be almost probably waste of time, but going through explaining what is spectrum would probably take quite a long time and distract more people, because it's a relatively technical thing. So, a short summary. So, for speech signal analysis, we use various signal processing techniques. We've just shown 2 of them. There are millions of them, of course. You can study signal processing as the major master at the university. So there is hundreds of different techniques. As we were saying, computing intensity contour is kind of easy. There's a formula for that, and it's reliable, and it's what you see is what you get. Extracting F0 contour is a bit more difficult and a little bit less reliable, because we are relying on an algorithm rather than on a formula. Algorithm also means that you have to manually set all sort of thresholds. You have to say all sort of plausible values and what is acceptance of this correlation and what have you. So, you might get those values a little bit wrong, or almost for every possible setting of the values, you will find speech signal which sort of violates those values, which would require different values. So, I just wanted to talk about the principles of signal analysis so that we just get into this mode of thinking about signal and think about numbers. But of course, we normally don't have to worry about the principles of signal analysis. It's good to have these warning lights for some of them, but luckily there are machines which do that for us. This is exactly the type of things which machines are good at. So we can of course use dedicated applications like Praat, which all of us, I guess most of us use, or we can use some signal processing libraries of our favorite language, like Python, for example, we are going to be using in this course, or actually something in between. So there are these libraries like Parselmouth and TGT, which actually act as an interface between Python and Praat. So they essentially call Praat routines through the Python interface. So you can actually operate Praat from your Python code. Why would we do that? It's because Praat is really, really good. It's really good. The signal processing in Praat is absolutely top-notch, in particular when it comes to speech signal processing. The signal processing which is specially fine-tuned and dedicated to speech. So that's why actually, I mean, my own experience, using sort of running signal analysis through Praat, through Parselmouth, is superior to running some native Python libraries for the sound processing when it comes to speech. But it might be, people might have different experiences as well. Cool. So let's take now, it's 1:30. Let's take 10 minutes break again until 1:45, and then we continue. Mm-hmm. Oh, sorry, questions? Yes?
Sir, according to the, for phonetic analysis, it is considered that sampling rate of 44.1 kilohertz is considered ideal, but there are field recorders which can record up to 192 kilohertz. So why can't we record on that parameter and only at 44.1 kilohertz? Like, is there any significance of this sampling rate? Yeah.
So what is the benefit of recording something at a very high sampling frequency? So when we record something at the 44,100 sampling frequency, so it means we have 44,000 samples and 100 samples per second, what type of frequencies which are present in a signal we can actually extract from the signal? We can see that they are present. So if we have 44 kilohertz plus minus sampling rate, and we want to record some crazy sound, this probably would be some ultrasound already, which is sort of whatever, 200,000 hertz frequency, we cannot record that sound with this sort of 44,000 sampling frequency. So let's imagine that we record 50 hertz sampling frequency. So only 50 samples per second. Can we record the sound which is 1000 hertz, which contains 1000 hertz frequency? Well, we cannot, because we have so few samples that a lot happens between those samples, which we will never see in the recordings, if you know what I mean. So what is the highest frequency which we can actually record for a given sampling rate? It's a half of the sampling rate. It's called Nyquist frequency. So, or Nyquist frequency maybe. I sort of pronounced the name in a Swedish way, but he was actually not a Swede, he was American. So for 44,100 hertz, the Nyquist frequency is 22,050 hertz. That's so we can record things up to that frequency. Now, what does it mean? It means that it's usually good enough for just about anything which our ear can hear, because we cannot really hear most of, well, in my age, I just get about 10,000 hertz or something like that, if I'm lucky. But most people, most sounds we actually do not simply hear. We are not bats. We do not hear the sounds with 20,000 hertz frequency. So from the point of view of processing the sound data, speech sound data, and extracting information relevant for human auditory capabilities, we don't really need high frequencies. As a matter of fact, a lot of machine learning, for example, is done because, the higher sampling frequency, the more data you feed to the machine, right? So a lot of machine learning thing is done on 18 kilohertz, 18,000 samples per second. 16 sometimes, yeah. even 16. There was actually, what was the old phone?
8K.
Yeah, old phone, because a phone is actually, as our colleague says, you know, my colleague always says when you talk to a phone with your mother, you actually don't talk to the mother, you are talking to a synthesizer. Because mother's phone encodes her speech, sends it in some phonetic features, as a matter of fact, over the network. Your phone receives it, decodes it, and synthesizes it back. So again, because your bandwidth was not so massive, and even with this encoding and decoding, you know, people only recorded, you know, the only 8,000, the sampling frequency was 8,000 hertz. So it only rendered sounds up to 4,000 hertz. So even some frication, some sh contrasts in some Slavic languages might have been lost in the transmission. So it depends on what you need to. But for just about anything we can hear, 44 is a plenty. 24 would be enough. But of course, if you want to analyze something, where the auditory apparatus for the humans is not necessarily the limit. We want, you know, some other animal, you know, perception stuff, what other animals, bats or whatever, then you would of course need higher sampling rate. It's a very, very long answer for a very short question, again.
Yeah, another point there is that actually, like, you know, it doesn't matter what is your sampling frequency, but if is your input device capable of capturing that or not, because most of our microphones are basically from 50 hertz to, let's say, 20,000 hertz. And
exactly.
you are asking that 44,100, anyway you're losing 50 hertz there. It is
Exactly.
already being cut off.
And I guess it works on the other side also. What are the speakers capable of playing? What is a range where they feel comfortable to vibrate, actually, and all that, yeah.
And then, of course, the space is one of the issues. Not anymore, but still.
Yeah. But of course, I'm sure that there are some scientists, not speech scientists, but some other sound scientists, maybe animal communication, which surely bat scientists must use something like that. If there was sort of new system evolve, you know, which can record frequencies to that level, all the bat scientists went, you know, that was the Christmas for them.
So we have a few microphones for elephants, actually.
Oh yeah, which need the low frequency
Yeah,
then.
low to all the way to 50K, actually 0.05 to 50K.
There is actually rather interesting, like this isn't just a chat. The interesting sort of phenomena we use these wavelet type of analysis, which is a sort of similar family of the spectral analysis, which we had on the previous slide, but works on slightly different principles. Can kind of work on a much bigger range of frequencies, because there are some limits on what frequencies, based on the window size, you can actually use for the Fourier analysis, which is beyond the spectra. So we use these wavelets, so we could analyze speech waveforms on much larger frequency scale. We are not talking about the high frequencies, but the low frequencies. So we could actually look at prosodic phenomena. We could look at the frequencies, you know, related to, let's say, syllables and even words and phrases and things like that. You know, all of those rhythmic characteristics. That's where we were looking at. And so we could plot these. I have some pictures of that, but not here with me. The frequency sort of spectrogram-like, or scaleogram as it's called, ranging from whatever 20,000, but down to 1 hertz, or even below 1 hertz. And what was actually rather interesting, there was all sort of things happening at every part of the spectrum. Apart from that, there was almost a blank gap between something like 10 and 30 or 25 hertz. There was almost no energy in that gap. And that's rather interesting, because that's the space, frequency domain, space, where our perception changes from hearing thumping to hearing a tone. If you increase the frequency of some drum-like sound, and you go faster and faster and faster, around whatever 20 hertz, depending on the person, you stop hearing drumming and start hearing the low tone. So this is the sort of range where our perception is ambiguous about the things. That's what's actually astonishing, is that human speech does not use that range at all, because that's something which we are not very good at. at sort of distinguishing or are ambiguous. So this might be very sort of anecdotal observation, but it was fascinating to see how these frequencies actually are matching our perceptual apparatus and our abilities to produce things. How sort of optimal in that sense human speech is, how you really feel every nook and in a very sort of efficient way.